So realize that that CCO cytochrome is a really big deal. And it turns out what happens when you leave atavism on, Warburg metabolism, but you never get to the regeneration pathway. That's actually oncogenesis.
Hmm.
And that's effectively what's happening in the world today. Why? Because it turns out blue light and non-native EMF, remember I told you the story before that light is able to photooxidize the oxidation state of iron. That
Yes.
means it'll keep it in the +3 state too long, so you never get to the +2 state. And
Mhm.
it
And the
turns
plus
out,
two is what you need to move oxygen around and stuff.
right, that's how you get back from a hypoxic state to an
Yep.
oxygenation state. Now, here's the part of the story that I
So
know.
okay, so because of blue light and other things, people go
Well,
from F2.
that's the external stuff. Let me go for a little bit.
Okay, okay.
So that's the external part because I'm weaving the story. So let's get back to your original question because I don't want you to think Uncle Jack forgot you. So do you know that leptin has got an absorption and emission spectra that starts at 220 nanometers? That should stop you hard in your track if you're a biochemist and go, wait a minute. I learned when I was in 6th grade from NASA that the sun only emits 250 to about 3100.
Hmm.
So why in the hell would we put our major hormone in our sub-Q fat there if it's got a 220 nanometer absorption spectra? Something doesn't fit here. Well, it turns out it does fit because there's this physicist in the 1950s and 60s who finds out that through the process of mitochondrial metabolism that we make light inside of us from oxygen radicals and from nitric radicals, RNS and ROS. His name is Fritz Popp. What does he decide to do? Fritz Popp takes every living tissue and puts it in a photomultiplier and finds out that as mitochondrial metabolism alters through all the different pathways you're expert in and I'm expert in that we had to learn, that it has a spectra of light that it emits. And it turns out the glycolytic pathways release 200 to about 1,000. And it turns out when your TCA cycle, you make a lot of extreme low frequency UV biophotons. In other words, the spectrum changes as metabolism changes. And it turns out, remember what I told you before, that light is capable of changing the oxidation state of iron by itself?
Yes.
Well, that was really important in the story in the GOE while we're innovating chlorophyll and hemoglobin. Because guess what? The original way we were doing it was with light, which is the reason why, Nick, now you're beginning to understand why Jack has such a disdain for food gurus and biochemists, because they don't understand that you don't need food. You don't need it at all when you understand that light changes the oxidation state. Then you have to ask yourself a question, well, wait a minute. If we create light inside of us, doesn't that change the game a bit about nitric oxide and what hemoglobin can do in a hypoxic event with oxygen? The answer is it does. And then it gets really interesting. This is the part I wanted to get to before you go further, because this is where the tables are really going to turn. Remember I told you before about Nick Lane and me coming at the problem through the different tunnels.
Yes.
I'm going to tell you, here's the big reason that this is a fractal. Is light from the sun the same as light from a mitochondria at the nanoscopic level, Nick? And I'm going to wait and let you think about it for a minute. Would you assume that it's the same?
I would, yeah, the natural assumption would be, yeah, it's light.
It's not. And it turns out the reason why is because of the inverse square law. Why? Because as the scale shrinks, light gets stronger. It doesn't get weaker. As scales get large, light gets weaker.
What do you mean weaker?
Just what I told you, that the amount of energy that it can impart reduces. So light at the smallest scales becomes incredibly strong. It's the same thing that happens with the electromagnetic force, strong and weak force in atoms. So it turns out light that's at the nanoscopic level can target different things. So you'll probably be shocked to know that light that's between 625 and 635 can actually take cyanide and move it off the electron chain transport. You don't need anything else to do it, but it has to be monochromatic laser light. So what am I telling you about these biophotons that are made in us? They actually make the biophotons that actually marry up to 220 light for leptin. Here's the other magical thing. Do you know that the key biochemical that you learned about in the intermitochondrial membrane, which is NAD, NAD is made out of what? Tryptophan. Do you know what tryptophan's absorption emission spectrum is?
No.
200, 400 nanometer light.
Right in that range.
Did you know that dopamine is also 240 to 420, also in the UV range? Turns out that all the aromatic amino acids absorb light that's stronger than our sun, that it turns out when our TCA cycle is active, makes 200 to 400 nanometer light. And that's been published, just so you know, in the literature since the 1960s. But Nick, I can tell from your face, you're like, Jack, I didn't learn that in biochemistry.
Yeah, I mean, yes, no one talks about this.
Well, guess what? You're going to go back when you do your deep dive, and you're going to see when Rick invited me on to talk to Huberman to be the teacher and him be the student. I asked him one question. I said, your journey through quantum biology should begin in 1927. I said, there's a guy named Alexander Gurwitch who is a Russian biophysicist. He took an onion root, cut it in half, put a piece of glass in between them, and nothing happened. Then he put a piece of quartz between the onion root, and you know what he found? He got mitosis in the other side. Do you know why that happened, Nick? Quartz allows UV light to penetrate it. And guess what he found? That UV light stimulates mitosis to go through the cell cycle. Do you think this might have any implications for the story that I told you, that light is the real cause of oncogenesis? Why? Because light can change the paramagnetic switch of +3 to +2 on iron and then get rid of nitric oxide. In other words, I just showed you how a baby goes from a sperm and an egg, comes together, releases light through the zinc release, which is a dopant. And what happens? The baby stays hypoxic in a Warburg shift in metabolism with nucleated red blood cells. The entire child becomes 9 pounds after 9 months, builds out all its organ systems by utilizing the biophotons created there. Why? Because those biophotons are massively powered. Why? Because they're at the smallest scales. So guess what happens? Becker comes along and says, okay, why do mammal regeneration suck? Because you mentioned earlier, we have great regeneration in bone and great regeneration in our liver. You should do a hard stop and realize, where do those nucleated fetal red blood cells really come from in mama? Where's that umbilical cord connect to? Oh, the liver, doesn't it? Right? Through the falciparum ligament and all those ligaments you learned in anatomy. And you're like, yeah, what the hell is the purpose of this? Why does everybody have a belly button? It turns out that ties to this story too. So Becker realizes that the DC electric current has to be augmented some way. The augmentation is what you started the podcast with me earlier. You said, Jack, I want to have a discussion about the leptin-melanocortin pathway. Well, guess how you get the rest of the regeneration program? Turns out the sun's light is the part that's missing, that we don't have, that salamanders have, that frogs have, that everybody else has. Why? Because it turns out when melanin is hydrated by that deuterium depleted water, it takes a current and down regulates it to 1/1,000,000th of 1 ampere. Guess what the size of the current was in Becker's work that dedifferentiated a red blood cell in us? 1/1,000,000th of 1 ampere. So guess what? It turns out that the leptin-melanocortin pathway is actually the regeneration loop. This is the evolution of CCO in hemoglobin that you just saw recapitulate in the leptin-melanocortin pathway. And what does that mean for mammals?